Hello students, in today's lecture we will study about Compton effect in quantum mechanics. Now quantum effect tells us about the change in wavelength that is undergone by a particle when it is getting scattered. A.H. Compton in the year 1921, when he was studying about monochromatic X-rays scattered by carbon atoms, found that when a beam of high energy incident photons, which can be X-rays, gamma rays, etc., are incident on a target which is rich in electrons, then scattering takes place and a change in wavelength is observed. Now, scattering could be of two types. Coherent scattering. In this scattering, no change in wavelength or frequency is observed. And in the incoherent scattering, a change in wavelength or frequency is observed, which is known as Compton effect. And it is mathematically given by del lambda is equal to h upon m naught c into 1 minus cos phi, where h is Planck's constant, m naught is rest mass, and c is the velocity. Classical physics failed to explain this. Quantum physics was very easily able to explain why this happened, that why these photons are behaving like particles, and the scattering is happening because of elastic collision. This concept of photons behaving like particles and the phenomena of scattering due to elastic collision between a photon and an electron, which is here is at rest, is basically totaling up the whole of Compton effect, and the photons scattered in the direction will be having lower frequency or longer wavelength than the incident photons. This is one of the strongest evidence in support of Planck's theory of radiation. Planck's theory of radiation. This Compton effect gives a very good support to this concept. Now, before we begin to derive an expression for Compton shift or Compton wavelength del h upon m del lambda h upon m naught c into 1 minus cos phi, we will begin by setting up this diagram. Let us understand. Here is my incident photon or my high energy beam, which is having energy E equal to h mu from Einstein's concept, momentum P equal to h mu upon c. This gets incident on the target electron, which is at rest. At rest means its velocity is 0, and at rest its energy is E equal to m naught c square. And since it is at rest, the momentum is given by P is equal to mv. V is 0, so P is equal to 0. After collision, this gets scattered in the direction theta and recoiled in the direction phi. So the scattered photon will have energy E equal to h mu dash. Momentum P dash is equal to h mu dash upon c. Now we will use the concept of energy conservation, which states that energy before collision is equal to energy after collision. So h mu plus m naught c square. H mu plus m naught c square is equal to h mu dash plus mc square before and after. Similarly, for momentum before collision, from law of conservation of momentum, momentum remains conserved. So, before collision and after collision, we will resolve momentum in the horizontal and vertical direction. So, when it will be in the horizontal direction, the cos terms will be there. When it will be in the vertical direction, the sine terms are going to be there. So, direction along incidence C, H mu upon C plus, here horizontal component is 0, equal to H mu dash upon C cos theta and cos phi. Both the cos components have been taken. For direction perpendicular, once it is sine theta this direction minus, because sine phi is in this direction. Now, we will take these three equations, h mu plus m naught c square equal to h mu dash plus mc square, h mu upon c equal to h mu dash upon c cos theta plus mv cos phi, and h mu dash upon c sin theta minus mv sin phi equal to 0, and solve them in a very tricky manner using many mathematical formulas and conclude the expression for Compton shift. What are we going to do? We will use the formula sine square phi plus cos square phi is equal to 1. This is a mathematical formula. So, in this expression, these two expressions, we will get the phi terms this side and the theta terms that side, and we will square and add them. We will get an expression, and then we will use this equation and the squaring adding of these two terms, the other equation, and solve those two equations to get this expression. So let us begin to solve it quickly. How are we going to do it? We will solve these three expressions to get an equation for change in wavelength of lambda, or the change Compton effect formula. So we will write all the three equations of momentum and energy first, then second we will square and add, so that sine square theta plus cos square theta becomes equal to 1. So let us begin. mv cos phi is equal to h mu upon c minus h mu dash upon c cos theta. mv cos phi can also be written as, we are taking h upon c common, into mu minus mu dash cos theta. And the second expression, mv sin phi is equal to h mu dash upon c sin theta. Now we will square and add these two equations and get c square on the right hand side. Squaring and adding cos square theta plus sin square theta will come equal to 1. So this becomes m square v square into cos square phi plus sin square phi is equal to h square upon c square mu minus mu dash cos theta whole square plus h mu dash square upon c square sin square theta. Now this sin square theta plus cos square phi is equal to 1, and this c square and this c square have been brought this side. So we get m square v square c square is equal to h square into a minus b whole square is equal to a square plus b square minus 2ab. So we get a square plus b square minus 2ab plus h square mu dash square sine square theta. Now what we will do, we will simplify this all the former further, and we will take h square common from the whole expression, and we get m square v square c square is equal to h square into mu square plus mu dash square sine square theta and cos square theta. These two terms again become equal to 1, and we are left with minus 2 mu dash cos theta. This term sine square theta cos square theta has gone reduced to 1, and we are left with this much inside. And from our energy equation, what did we have? We had h mu plus m naught c square is equal to h mu dash plus m c square. Now we will take mc square term this side, and this expression we will take it that side. Why are we doing it? We are doing it so that mc square we get this side, and we are already having this expression. Then we will simplify them. So the next trick is to get mc square this side. Then we get mc square is equal to h mu dash minus h mu minus m naught c square, right? And we can also write this as mc square is equal to h into, we can take minus sign common and make it mu minus mu dash, so that this minus becomes plus m naught c square. Now we are going to square this. Why are we squaring it? What have we actually done? We have taken minus common throughout, so this has become plus. Now we are squaring it so that this expression reduces to this form here. So we get, on squaring, m square c to the power of 4 is equal to h into mu minus mu dash plus m naught c square to the power square. Now we will open this. A plus b whole square is equal to a square plus b square plus 2ab. So on opening this, we get m square c to the power of 4 is equal to h square into mu minus mu dash square plus m naught square c to the power of 4 plus 2h mu minus mu dash into m naught c square. Now what we will do is, we will further simplify this expression a little more, so that here this m square v square c square which we had, we will simplify that and we will take this expression. So this and this. Now we are going to take only these two expressions, and we will subtract m square c to the power of 4 minus m square v square c square. So this expression and this expression we are going to subtract. Once we subtract, what are we left with? We will subtract these two equations, and what are we getting after subtracting them? We subtract the two equations and we get m square c to the power of 4 minus m square v square c to the power of c square is equal to minus 2h square mu dash plus m naught square c to the power of 4 plus 2h m naught c square mu minus 2h mu dash m naught c square plus 2 mu dash cos theta h square. So this becomes m square c square into c square minus v square is equal to 2h square mu dash cos theta minus 1. We have purposely done it. We took the negative sign common along with it so that the formula becomes easy for us, plus 2h m naught c square into mu minus mu dash plus m naught square c to the power of 4. Now what we will do is, we here will use the relativistic mass. Relativistic mass, that is m equal to m naught upon under root 1 minus v square by c square. So putting this value here, we get m naught square upon under root 1 minus v square by c square into c square minus v square is equal to 2h square mu dash cos theta minus 1 plus 2h m naught c square into mu minus mu dash plus m naught square c to the power of 4. Now we will simplify this further. We get, this is under root, so squaring that you get back this quantity only, m naught square c square into c square minus v square upon c square minus v square into c square is equal to 2h square mu dash into cos theta minus 1 plus 2h m naught c square into mu minus mu dash plus m naught square c to the power of 4. This and this gets cancelled. This c square becomes c to the power of 4. So this is m naught square c to the power of 4. This also gets cancelled with this. And what are we left with? We are left with 2h square mu dash into 1 minus cos theta is equal to 2h m naught c square into mu minus mu dash. Now let us see what else can we get cancelled. We get 2 cancelled, 1h gets cancelled. So what does this expression reduce to? It reduces to mu minus mu dash upon mu dash is equal to m naught c square into 1 minus cos theta h. We will simplify this further. We will simplify this expression further. What do we get on simplifying it further? We will simplify it further and we get h into 1 minus cos theta upon m naught c square is equal to mu dash upon mu minus mu dash. So h upon m naught c square into 1 minus cos theta is equal to 1 upon mu dash minus 1 upon mu. Now note certain things in this expression, that this m naught rest mass is a constant, velocity of light is a constant, Planck's constant is h. So it is depending upon cos theta, the Compton shift or the frequency. So let us simplify it further. H we can write upon m naught c. 1 c we will take it this side because we will use the formula velocity is equal to frequency into wavelength. So into 1 minus cos theta is equal to c upon mu dash minus c upon mu. Right? And then we know that this is equal to del lambda. So del lambda is lambda dash minus lambda. V is equal to mu into lambda. So this formula becomes equal to h upon m naught c into 1 minus cos theta. And we know from formula that cos 2 theta is equal to 1 minus 2 sine square theta. Therefore, del lambda is equal to h upon m naught c into 1 minus cos theta can also be written as cos 2 theta. So that becomes sine square theta. Okay. So this is h upon, this can be written as del h is equal to 2h upon m naught c into sine square theta by 2. Both are correct. You can very well write any of these equations. They both are correct. This is correct. This is correct. Have a look. Compton shift is only depending upon angle of scattering. If theta is equal to 0, then del lambda is equal to 0 is 1, so it becomes 0. That means no scattering is going to happen. Everything is depending upon the angle of scattering. When theta is equal to pi by 2, del lambda is equal to h upon m naught c, which is equal to 0.0242 angstrom. And this quantity h upon m naught c is known as Compton wavelength. It is known as Compton wavelength, and it is third when theta is equal to pi, del lambda is equal to 0.048528 angstrom. The Compton shift is less than 0.001% of the initial wavelength of visible light. Therefore, Compton shift is undetectable in visible light. We are not able to see Compton shift in visible light. We cannot see because it is very small, and as the angle theta varies from 0 to 180 degree, wavelength of scattering photon also varies from lambda to lambda plus 2h upon m naught c. Thank you.